You routinely hear in your drugstore discussions. For example, amphetamine. This is amphetamine. Okay, pretty simple structure, yeah? It's about 8 or 9 carbons, an amino group, okay? But it's a stimulant, okay? And actually, like Adderall or something is just basically amphetamine, yeah? We're giving it a brand name. We can look at other things. But amphetamine with an OH on the carbon, the benzylic carbon, that's phenylpropanol amine. Phenylpropanol, 1, 2, 3, that's propanol amine. Of course, there could be isomers, and if you gave it IUPAC name, you would probably get some numbers. It's like 1 phenyl, 2 amino propane, or okay, but the name works. PPA is a common abbreviation. PPA you can buy at the counter when you pay for your gas. It's like no-dose pills or something. Okay, it's a stimulant. It's also used in some diet pills, just to hype you up, get you going and bouncing around, stuff like that. So it's legal. Amphetamine typically you can't buy at Walmart. Because it's more active, it's more potent. Okay? One reason is, see this OH group makes the compound more polar. And with more polar, it doesn't get into the brain as quickly. Because there's a blood-brain barrier. It's about right here. And compounds sort of have some lipophilic nature to get past that lipophilic barrier. And this doesn't get into the brain as easily. This gets it more into the brain and the CNS, and it has more CNS activity. Okay? Now, the analogous over there is just where you put methyls on the nitrogen. If you put a methyl on the nitrogen of PPA, you get this here, which is Sudafed. Okay? And it's legal. It's decongestion. Now, if you have a methyl without the OH, well, that's methamphetamine. Amphetamine, you put a methyl on it, methamphetamine. So the ones on the bottom are not legal. The ones on the bottom are more active because they don't have the OH. Well, of course, people who want to make methamphetamine used to buy a lot of Sudafed at the drugstore, and they could do chemistry and basically remove that oxygen. And that's the meth lab approach. There's some ways to do that. I think like phosphorus, iodide, PI3, it's no chemistry we've ever looked at. But that's reduction. To make meth, and again, without the OH, it gets into the CNS, and it's a really potent CNS compound. So, well, how can we make methamphetamine other than just removing the OH from Sudafed? Well, using our reductive amination approach, we can do it. Because reductive amination is what? It's a way to make alkylated amines. Starting with amine that has one less alkyl group. Okay, you got to think about this synthetically. What does the reaction do and give, etc. On the previous page, let's go back. Now this is at the bottom of a previous page. Now I put the aldehyde as the key thing here, but if we focus in on the amine as the key thing, and then look at this amine, we've added the alkyl group to it, a benzyl in this case. How did we do that? The benzyl basically came in as a carbonyl, we made the imine, and then we reduced it. But look at this, let's go backwards. If you wanted to make this using this approach, you would say, hey, one of the R groups, this one is defined, so we'll look at this one. We can go back to, instead of N single bond to carbon, we go back to what? N double bond to carbon. It's drawn differently, but it's now N double bond to carbon. So you say, hey, and if we go back, is that an oxidation or reduction?
Oxidation.
Yes, this way we're adding H's. That's reduction. This way we're removing H's, so that's generically oxidation. So you say, hey, I'm going to oxidize this back, put the double bond in, remove the two H's, for here we added two H's, go to the imine, and after the imine, what's the next step in going that way? Hydrolysis. You add water, you know, you can have an H plus catalyst, you can add H3O plus. What does that do? It splits your imine into the amine, and what does this carbon become? Carbonyl, because how do you make imines? Amine plus carbonyl. So hydrolysis splits it back to the amine plus the carbonyl. So you can think about going backwards. I'm going to go back to the imine, and then I can separate that into the amine plus the carbonyl. Let's see if we can do that here. So methamphetamine. Now you actually have two choices because the nitrogen's bonded to two carbons. I'll do one for you, then let's see if y'all can sort of do the other. Well, let's say this is the R group. So instead of N single bond to carbon, what do you want to envision?
Double bond.
Yeah, so let's go back to boom, boom, boom. Double bond to carbon, I mean to nitrogen, or either way you want to say it. Does that look right? We go back to the imine?
Yeah.
Because if we went this way, we would just need to reduce it. Okay, so we're going backwards. And now if we keep going backwards, that would go back to what? Amine and carbonyl, because that's how you get the imine. So this would go back to boom, 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 plus what? Methylamine. So if we came forward, these two would react to get imine, then we reduce it to the single bond. So there's your approach. You take this ketone, the methylamine, you make the imine, you may not even want to isolate it, then how do you want to reduce it? Give me a reagent.
Hydrogen gas.
Hydrogen gas will work with like nickel or palladium. What else?
NaBH4.
Again, that would have problems because that would reduce ketone.
NaCN-BH3.
Yes, sodium cyanoborohydride would not reduce ketone. Sodium cyanoborohydride is expensive though. That's one reason that in lab we first isolated the imine. Then you react that with sodium borohydride. Also in lab, using hydrogen gas is just difficult for 20 or 30 students to use hydrogen gas. But on the show Breaking Bad, didn't they, at one time, they were breaking into a chemical company, and what were they trying to steal? Methylamine, were they?
Yeah. I don't know.
And they also mentioned this compound. They called, this was phenyl acetone or something. Or, they mentioned this compound. So they were actually doing sophisticated chemistry, not just the old meth lab approach of removing Sudafed, the oxygen from Sudafed. But they were trying to steal methylamine at one point on the show. A big tank of it, because methylamine's a gas. So they were doing this chemistry. I don't know what they were reducing it with. But this compound right here, is methylamine. Now, if I tried to order like a kilogram of this for teaching the lab, they would red flag it. Okay? You're going to have to fill out a form saying this is only going to be used for teaching purposes, etc. Because they know that people will buy this to do this. Okay, so that's one approach. What would be a second way to do a reductive amination? Instead of looking over here, let's look over there. Take a minute and do the approach to make the carbon on the other side. Bring it in. What would be the starting materials there? We can go back to this is going to look funny because it's one carbon. What's on this carbon? Anything on the carbon? Yeah, it's just two H's. When we oxidize it back to the amine, then this splits apart because amines, we're under Roman numeral 2 still. Everything's reversible back to what? The carbonyl plus the, it's going to give what? The amine plus what? Oh, what's the carbonyl? Just that. And what do you call that? Formaldehyde. One carbon. If that was a OH, it'd be formic acid. That's formaldehyde. Yeah, you take these, you make the amine, you can come this way. But somebody said it, what is actually this though? Called? Amphetamine. Amphetamine. Yeah, you can actually take amphetamine and put the methyl on by a reductive amination sequence. Of course, somebody may also propose, hey, well, why don't we just react amphetamine with methyl iodide? Would that theoretically work? Yeah, you could just do like an SN2 and methylate this, and then you use something to pick up the AHI. But that's a direct alkylation, and again, what type of problems do you have with that? Yeah, because once you get methamphetamine and there's methyl iodide still around, it can just alkylate again, and you'll end up with multiple alkyl group on your nitrogen. So direct alkylation has that problem of polyalkylation. But it's theoretically just a good old SN2 reaction. Dimethylamphetamine? I'm sure that compound is known, I don't know anything about it. Sometimes those things are less active because the nitrogen gets too sterically hindered and it's not as nucleophilic and basic and stuff. So it may not be as potent as a CNS agent.
Can you use a dye ball to remove the hydroxy group on the Sudafed?
Dibol, well, dibol is H- source.
Right.
You'd probably need some type of acid to make the OH a better leaving group. That type of chemistry is known. A lot of times you use a Lewis acid, like dibol and BF3 or something. Sometimes you can reduce off OH groups with hydride sources. There's chemistry like that. But that's a good, you're thinking mechanistically, you need like an H- to come in and replace the OH. When you get into that type of thinking, there's so much out there that can be done. Okay. Now, this idea of going backwards is really just for us doing synthetic analysis, retrosynthetic analysis. Because it's actually in the lab pretty difficult to go back to the amine. But in the body, it can be done. The body is a lean-mean oxidizing machine. And the body routinely does this going backwards. And this is actually seen in drug metabolism a lot. And if you look at the handout, the white handout, I believe, the one you printed on your own, and we're fixing to look at that with a Wittig. So on the back of the carbohydrate page, oxidative dealkylation of amines in the body is a very common metabolism of drugs. Very common process for metabolizing drugs that you may take, or any other xenobiotic that enters your body. For example, amphetamine, it could be a drug you take. Your body will actually oxidize it and put the double bond in. Again, make sure you know oxidation. There's two ways to judge oxidation. Adding oxygen. Did we add oxygen when we did this to the molecule? No. But there's another way to judge oxidation. Removing H's. That's what we've done. We've lost 2 H's. Removing H's is oxidation. Adding H's is what? Yes. So this is an oxidation. Your body can do this. Once you get to imine, what's it prone to do with lots of water and acid? Which your body has lots of water. There's plenty of acid catalysts or even enzymes that can catalyze reactions. Go back to the carbonyl compound plus the amine. Okay. So your body can do this, and it's well known that if you take amphetamine, that this will be present in the urine, etc. Now, how much? Actually, the pharmacology book I have shows different routes of metabolism for amphetamine. This is just one possible route. And it actually gets into species, and I haven't looked at this book in a while, but I know something about the rabbit. It says, I think the rabbit does this metabolism a lot, or maybe in humans it does something else, I can't remember. But different species give different metabolism outcomes. But this is certainly one of them. And a lot of times when you pharmacologists or like people are inspecting urine for metabolites, you got to understand what are potential metabolites. If you want to understand the chemistry. So this is just the reverse of the reductive amination. And what ultimately happened? Why do we call it dealkylation? Because here the nitrogen has an alkyl group bonded to it. Well, now it's gone. It was dealkylated in the process. Imipramine, here's just another example. It's a tricyclic antidepressant. It's tricyclic because it's 1, 2, 3. Tricyclic. It's got this nitrogen here, but this is sort of a basic side chain. It's dimethyl. But in the body, one of the methyls is removed. It's demethylated or dealkylated. Well, guess how?
Oxidation.
Oxidation to the amine and then hydrolysis, just like above. Okay? Now, for this particular drug, this is actually not active as an antidepressant. It's only active once the body removes one methyl. And so what you take is not actually active. This is thus called a prodrug. Prodrugs are drugs that are not active themselves, but they have to be metabolized, then they become active. Now, desipramine can also just be take that. But I think what happened is they found that this was active first, and then later on found out that it wasn't because of this compound, but it was because it was being metabolized. And so then you could say, well, let's just give desipramine. That's sort of like, remember the first antibiotic, the dye that when it was metabolized, it led to sulfanilamide? That handout? So originally they thought the dye was active, but it actually wasn't. It was getting metabolized and releasing sulfanilamide, and that's what was actually active. Once they figured that out, they no longer gave the dye, they just gave sulfanilamide.
Does one like work faster than the other since your body doesn't have to metabolize it, or is it so fast it doesn't?
It's potential, but then you may say, well, why are any drugs given as prodrugs? Sometimes, see, if you get into pharmacology and medicinal chemistry, you learn, well, why use prodrugs? Maybe this compound is absorbed into the bloodstream for some reason faster. And then once it gets into the bloodstream, then you let it get converted. There's lots of reasons. For example, here's one that's more maybe relevant. There's one compound out there that is given to infants and small children, and it has to be given as a liquid, like in a spoon, but it tastes terrible. So, okay. So guess what? Instead of giving that compound, they give a prodrug, which has a much better taste. When it gets into the body, it gets converted to the active form. So that's just to make it more palatable. There's lots of reasons you might use prodrugs. Okay. metabolism, I think we covered F and G. I think we're to the Wittig, which the Wittig is written on the white handout. Okay, Wittig, one of the top 10 reactions in organic chemistry, and I'm not kidding. It's one of the few that has actually won Nobel Prize in 1979. Actually, Wittig shared the Nobel Prize with A.C. Brown, who developed sodium chlorhydride. Okay. Wittig, German chemist. Brown, since maybe foreign-born, but always worked at Purdue. And was there a long time. Wittig died in the 80s. A.C. Brown died about 10 years ago. Did I tell you all that I actually saw A.C. Brown one time at a meeting? Yeah. He was very old, old. This was in 2001 in San Diego. He died in like 2004. Can I tell you all that? It's just kind of interesting. I was sitting on the payphone outside of the bathroom. Have you ever used a payphone? Yeah. Okay. I stand there, and then he walks out from the bathroom. And he stands like right there, and I'm like on the phone. And so he looks at me, I kind of nodded at him, and like, I knew he was. Kind of nodded back, he just kind of stood there, you know. I was talking. And then his wife walks out of the ladies' bathroom, and then they walk up. So that's my A.C. Brown story. I never met Wittig. Really didn't really meet A.C. Brown, did I? Okay, the Wittig reaction looks like Wittig, but we pronounce it Wittig. At least that's what the Germans tell us. It's a way to make alkenes from carbonyls. Okay? Way to make alkenes. And essentially, we're replacing the oxygen of the carbonyl with another carbon. And we're going to have a carbon-carbon double bond, which is alkene. Okay? Of course, when imine, you replace the oxygen with a nitrogen. Now we're replacing it with a carbon. For example, here, we replace this with a carbon double bond, and we may have a methyl on the carbon. And yeah, that's an alkene. Of course, you can have E and Z isomers with your alkene. Okay, what reagents do we use? It's this interesting phosphorus reagent. Phosphorus and then 3 phenyl groups bonded to it. And in this form, it's double bonded to a carbon. This can be generally referred to as a Wittig reagent, but it has 2 forms, whether it's been protonated or deprotonated. Now, we'll look at the mechanism. Let's first, I think, focus more on this here. It's called a phosphorus ylide. An ylide is a neutral compound. It's net neutral, but it has 2 different charges. So since it's net neutral, one charge is plus, one charge is minus. And the 2 charges are, does it say it right? They're next door to each other. They're next to each other. Does it say they're next to each other?
Yeah.
It doesn't say it, but they're next to each other. Okay. If they're not next to each other, it's not called an ylide, it's called something else, maybe a betaine. I think all of these that are dicharged are zwitterions. But ylides is where they're next door to each other. Where did that name come from, I don't really know. But there's 2 different resonance structures for your ylide. The one I show up there, which is this, there's no charge there. Now phosphorus is under nitrogen, so it makes 5 bonds. It's just like nitrogen. What's the charge of this phosphorus here? How many electrons does it own?
5.
It owns 5. It's in group 5. It's a neutral phosphorus. Of course, that carbon's neutral, and there's 1 H there. Of course, it better be neutral because I'm not showing any charges. If it was charged, I should show a charge, or I'm lying to you. So we need to know why these are neutral, why that's neutral. Now, how many electrons total around the phosphorus? 8 or more? More. Phosphorus can't have an expanded octet. Nitrogen can't, but phosphorus has d orbitals, and it can. Okay, so that's okay. Now, this is just a resonance structure here. We'll actually kind of get to this first when we make them, and then we'll go that way. But to go back this way, we take the 2 pi electrons and just move them over to phosphorus, which is probably more electronegative than carbon. Okay? What does that arrow movement give? No. No, that's actually the wrong way. That would put a long pair on phosphorus. Actually moving it the wrong way. So my dipole really doesn't make sense. That's why it's better to kind of start over there. Well, to go that way, we'd have to move them here. But very importantly, I hope everybody recognized how my arrow was wrong. My arrow movement would not give that. If I want a long pair on the carbon, I've got to move the pi electrons onto carbon. This is a resonance structure. Now, if you want to go that way, you just say, hey, what happened? These electrons were moved in to make a pi bond, and that puts you over to that resonance structure. Does everybody agree the only difference in these two is placement of pi electrons? Okay? Because this long pair is in a p orbital. So there's 2 different ways to show a compound where we only are showing changes in placement of pi electrons. And what do we call that? Resonance, okay? By the way, are y'all getting the idea of resonance? We started back in September. Is it sinking in any? Okay. So, if you show it like this, you see the dipolar nature and why it's called an illith. But most often you're going to see it drawn like this, in this form. Both forms are important. This form will be important for helping us just to predict our product. This is going to be important when we do mechanism, because we see more of the reactive nature. Okay, well let's look at the mechanism. And I'll use this here. Okay, this is the same thing, but let's use this. Carbonyl, nucleophiles like the tag. Do we have a nucleophile in this structure? Right here. These electrons add to carbonyl, electrons up. What are we going to get? Film. Electrons up is going to give us an O minus, yeah. There's a methyl there. What bonded to the carbon? We just made this bond. Carbon there that has a methyl and a phosphorus with 3 phenyls. That phosphorus is still plus. And is this charged? No. I mean, the electrons are now bonded there. How many H's on this carbon? Yeah, there's one there. There's one here. That's a standard tetravalent carbon, tetrahedral carbon. We get that. That's just a nucleophilic addition of this carbanion. Okay, what are we trying to ultimately do? We've got a single bond to carbon-carbon. This ultimately becomes a double bond, right? And we also know that in the reaction, this is produced as a byproduct. That oxygen ends up on the phosphorus. And that's called triphenylphosphine oxide. I should have drawn this a little bit differently, and hopefully you can erase. Instead of putting the oxygen here, let's put the oxygen here. It's still an O minus and a methyl coming off that carbon. But I just want the O minus closer to the phosphorus plus. They're going to be attracted to each other anyway, right? Don't pluses like minuses? And there's free rotation here. So this thing is going to, okay. Well, the next step is oxygen adds to phosphorus. It just adds, because phosphorus has d orbitals. Minuses like pluses. Also this, there are certain elements on the periodic table that just love each other. It goes back to ultimately just good thermodynamics. Oxygen and phosphorus love each other. Fluorine and silicon love each other. Okay? There's others that just have big love affairs.
Would a bond angle not be a problem?
We're going to look at that. What size ring are we actually making?
Or
It's actually going to be a 4-membered ring. What does this electron movement give? Let's assess the structure. Boom, 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 boom. Hold on. Is that really plus still?
no.
Let's don't be quick to charge. 2 lone pairs left. Is that neutral?
Yep.
Yeah, see, that's just standard oxygen. We did standard bonding back in day 1, right? Organic 1? Standard bonding. What's the charge of the phosphorus? How many does it own? It owns 5. It's now neutral. Yes, it has more than 8 electrons around it, but it can expand as high as 10. The important thing is you see why it's neutral. Everything's neutral there. And yes, that's a 4-membered ring. Okay? That does have a name. I don't think I wrote it down because it's not that common. Not going to even worry about it. Bond angles, yes. It's from 9th grade geometry, that's 90 degrees, right? Where it prefers 1 to 9.5. So it does have some angle strength. So why would it form then? Why would that form? They're in love. Well, they're in love, so it makes a strong bond. Also, minuses like pluses. So some things, sometimes good things override what we think is not so good. Well, this is known to be there. Well, this is the proposed mechanism that has pretty much been definitively confirmed. At this point, though, it is a strained ring. What happens here is sort of almost like a Diels-Alder where there's just some electron reorganization here. So it's a concerted process. I reckon I'll start with the oxygen lone pair. This oxygen wanted to make the bond to phosphorus, and it made 1. Well, guess what? It wants to make 2. Because guess what? It loves phosphorus. So these electrons say, I'm going to make another bond. Well, the phosphorus is like, hold on, I've already got a lot of electrons. I got to get rid of something. So these are sort of moved away, or however you want to say in your mechanistic language. Maybe shot out or something. But these move away from the phosphorus and actually come up here. Here's a single bond. Instead of bonding to phosphorus, phosphorus doesn't want me anymore, so I'm going to go make a what to the carbon? Double bond. That's all that happened. We moved the electrons up here to make a double bond. Well, this carbon can't have more than 4, so what happens? It's got to get rid of something. Well, these move over to oxygen to give the oxygen back its lone pair. And this is just a kind of a concerted, all in a ring. What do we call reactions that are concerted with a ring transition state? The Diels-Alder is an example of this type of reaction. Pericyclic. Pericyclic reactions are reactions that are cyclic and have a cyclic transition state. Now, I never show transition states. In books, you'll see transition states where this bond is starting to form, this bond is starting to break, and it'll show you partial charges. Okay? But it's all cyclic. And the Diels-Alder, right? If you do this, isn't it like electrons here, electrons here, electrons here? Well, this starts to form, and it ends up being a cyclic transition state. That's generally known as a pericyclic reaction. Okay? And a lot of books have chapters on pericyclic reactions. You'll find the Diels-Alder in that chapter. This is another example of that general idea. In the end, what does all this electron movement give? Yes, it gives products. Double bond between the two carbons. That carbon has a methyl and a phenyl. This carbon has just a methyl. And that's the product of this. But what do we produce here? Triphenylphosphine, double bond to O. That's your triphenylphosphine oxide. So it sort of adds, you get this love affair, you get this, and then it sort of collapses to give your products. Now, of course, your alkene can be E or Z. Which one's it going to be?
E.
It actually can be either. Okay. Basically, this has free rotation, and it's free. Once this does this, this is set, and maybe that is back and this is forward. Maybe at this point it collapses to an E or Z, but this can be either. There's nothing in here that's going to define stereochemistry. Your Wittig product can be E or Z, and you usually get mixtures. The starting comment is you usually get mixtures. But over the years, there's lots of development to the Wittig where you can get only one or the other. That's sort of beyond the scope of what we're doing here. We're just sort of introducing it. Okay? With many reactions, there's been lots of progress in tweaking it. There's some types of ilids that give more Z, et cetera, et cetera. Was there a question?
Yeah, I was just saying, like, isn't thermodynamically the E like always preferred? I know like it could be based on sport, but wouldn't like the activation should be lower if like the whatever like the phenyl was forward, so then like the
As an opening comment, yeah. I mean, thermodynamics, just from organic 1, trans typically more stable. But there can be a lot more going on.
Okay.
Because there's just so much more than we've ever discussed. Maybe, there's 2 phenyl rings here. And you say, well, these big rings are going to want to be trans. Yeah, but guess what? Phenyl rings like to interact because they sort of do this pi stacking. And that may promote cis. So there's lots of reasons where you may get the other thing because we haven't covered every possible scenario. Believe it or not, we're just sort of covering the basics. So in the end, there's other reasons why you might get the one that's not so thermodynamically stable. So something else was going on. Maybe there's some hydrogen bonding in there. We saw a couple of examples of that, right? Okay, what do we need to talk about here? There's a mechanism. Any questions about that? Well, we'll move on to formation of ilids. How do you make ilids? Pretty straightforward. Look at this down here. Triphenylphosphine. That's a solid. The phosphorus is very nucleophilic. It can react this with just like a carbon with a leaving group and do a good old SN2. Okay? And this will take place. It's a neutral phosphorus, but it's a good nucleophile. And we can get this form. Now, the phosphorus doesn't have an H to lose, and so it can't go neutral. And so this right here can be isolated. And actually, something like this is what we're using in lab. Remember yesterday, the one we're using in lab had a chlorine minus. Okay? Well, these are made from this type of just simple SN2 reaction. Now, some people call this the Wittig reagent, but it's actually not because there's no minus here. How are we going to get a minus there? You treat it with some type of base, then the alpha carbon, the next door carbon, whatever the base is, I'll use hydroxides, although traditionally it's usually a stronger base. This can take the H, leave the electrons behind, and then you have an anion over there. Now this is really truly your Wittig reagent because you can show the double bond resonance structure. Okay? Now in practice, you usually put this in your reaction and a base. And you generate the ylide in the reaction. And that's what we're doing in the lab. We're using a phosphonium salt and a base. What base are we using in the lab? We're actually using potassium phosphate in the lab as the base. It generates the ylide, and then the carbanion adds 4-membered ring. Y'all see the 4-membered ring yesterday when you were drowning? I don't know if that 4-member ring has ever been isolated. I would think it has not, because it probably collapses pretty quickly. But maybe if you do it at very cold temperature, somebody is actually isolated. Or maybe it's been observed by NMR or something. There's lots of probably good evidence. Okay, so we can put this all together and show maybe a line reaction like this. Well, here's kind of a phosphonium salt. Some base is going to generate the ylide. We've got a carbonyl compound that'll react there. What do we get? Here we go. Now, one thing I want you to make sure you recognize in terms of just predicting the product, let's look at this. If you draw the ylide in this form, what's going on here is just partners are trading. The phosphorus becomes double bonded to the oxygen, and this carbon becomes double bonded to that carbon. Right? This is a carbon with a phenyl and a methyl. Carbon with a phenyl and methyl. It's now double bonded to a carbon with a methyl. It's now double bonded to a carbon with a methyl. So to me, this resonance structure is very good for just seeing how they're hooked together. Okay? But if you're looking at this, such a reaction like down at the bottom, I would recommend saying, okay, what is the actual ylide in the double bond form? And it's going to look like this. Because we're going to make the anion, then we're going to do resonance structure, which is this. And once you see this, you see that the oxygen is going to be replaced with the carbon methyl. Question here, why phenyls on the phosphorus? Why not like methyl groups?
Localized charge.
I didn't quite hear you. Let me go ahead and tell you. Because if this was like methyls, when you did base, you would have a CH over here and over here. See, with phenyls, the bonded carbon doesn't have an H, and so there's no H's over there to remove with the base. So there's only H's on the other side. So phenyls are sort of inert. There's no acidic H on that carbon. So that's why you use triphenylphosphine and maybe not like trimethylphosphine. Okay, need to look at that, etc. Real quick, like I just told you, when you see it in this form, just show the product there. I mean, predicting product, if it's in this form, pretty darn easy. Boom, boom, boom. Double bond. Instead of oxygen, it's double bonded to what? A carbon with a what? Phenyl. Yeah. There you go. Plus what? Somebody said it. Plus what? Plus E. Because that is what? Z. Ethyl and phenyl are your priority groups on the same side. Yeah. But you're also going to get E. Those you'd have to separate. Now, sometimes they're easily separated by recrystallization, or sometimes they're not. Again, there's lots of times when a reaction may be pretty selective for some reason. Now you need to be able to use this in synthesis. Show Wittig synthesis of the following alkenes. Basically going backwards. One thing here, there's going to be choices. For example, if you look at this, in the product, isn't one of the carbons originally carbonyl? In this product, which was carbonyl, A or B? A. But actually, B could have been a carbonyl. Because this could have come from boom, boom, boom. That plus that. Wouldn't that have also given that? This is where you sort of reverse which is illid, which is carbonyl. Okay, here's the key thing. Typically, you want your illid carbon to be less substituted. So which would be better, the way they made it originally or this way? Original. Why is it better to have that less substituted? It all goes back to how you make it. You're using an SN2 to make it. So you would rather have your Wittig carbon to be the less substituted. So keep that in mind. What I would like you to do is do both ways. Each of these show two different Wittig approaches. And then let's determine which would be the best. We'll pick up there. Please think about below. Okay, we're ready to start the handout I sent you by email, which is our last handout. But it is a doozy. Have a good weekend. See some of you in lab. And look forward to getting your reports on Monday.